Hi everyone. Welcome back. And since, as I mentioned, the due date of homework 2 is postponed for another week, but if you finish it, you can feel free to turn it in right now. So today we'll continue our lecture, but starting from the reviewing of our last lecture. So the first thing, or the most important thing we discussed in the last lecture is about the Boltzmann's postulate. And also, I remember that somebody remind me that I misspelled Boltzmann's name. It should end with double N, not just a single N. But that's not directly related to the physics. But the Boltzmann's postulate is basically about how to understand the thermodynamic entropy from a microscopic point of view. So the postulate looks like this. And we discussed, as I mentioned, this is the thermodynamic entropy. And we discussed about the meaning of this absolute value of gamma. It is basically the volume of accessible phase space. Okay. And we also try to emphasize that this equality should be treated carefully. It just means up to subleading terms in N. And here N is the number of degrees of freedom that we are discussing about. Okay. So in order to understand Boltzmann's postulate, we basically introduce the concept of phase space. And for particle systems, it's quite easy to define it. Basically, we know that in order to describe the coordinates of our particles, we need to specify the coordinates for all the particles. So for example, we need to specify R1, R2 to Rn. Okay. So in principle, if we live in 3 dimensions, this is a vector with 3n components. And in addition to the position, we also know that in order to predict the motion of our system at the microscopic level, we also need to specify the momentum of each particle, which is now labeled by the momentum of the first particle, the second particle, to the momentum of the nth particle. And also, it is a 3n components vector. And the microscopic state, or the in order to specify our system uniquely, we need to define this Kc, which is a object that composed of the position R and the momentum P of all the particles in our system, which is now a 6n component vector. So now we define what is the phase space of our system. So we need to try to describe what do we mean by accessible. Okay. So in order to define the concept of accessible, we need to first define what is the concept of observable in this scenario. So as we mentioned, now our system can be described by a point in the phase space. And as time evolves, it could have some very complicated motion. Okay. And as the system is evolving, basically some quantity will fluctuate like crazy, and some quantity will basically remain more or less smooth. Okay. So suppose within this regime where basically our system evolve as a function of time, but if there's a function O, that's where the argument is the status of our system, you would map this this trajectory to a relatively smooth value. Then we said this O is a observable. So once we have this more or less mathematical definition about what is a observable, basically it's a function that maps the trajectory of our system in the phase space into a smooth value. Then we are able to postulate that basically all extensive thermodynamic variables are observables. Okay. So once we have this structure, then we are able to define what do we mean by accessible phase space. So basically, accessible phase space is basically defined by those extensive variables. Okay, which are observables. Then, to some extent, we give a well-defined description about Boltzmann's postulate. Then, as I mentioned, that the equality or this equality should be defined up to subleading terms in N. That also suggests that we could have different definitions of entropies. Okay. So in our last lecture, we give 3 of them, roughly defined by the extensive variables xi, and now this xi will be a function of our microscopic state, which is Kc. And now the first definition of entropy, we said that we consider the microscopic configurations in our phase space such that the value of this xi is defined within an experimental error delta xi. And then we consider those configurations as the accessible phase space volume, and we take a nature log of it times kBt. Then we got the entropy. Okay. And the second definition is quite similar, but actually we still use this xi of Kc as our axis. But now we include all the values ranging from the lower bound of our observable to the to xi. Okay. And the third definition is that we said that we only consider the states just nearby the xi. Okay. And the reason that these 3 different definitions of entropy will give us the same physics is because we live in a super high dimensional space, and all the weight of your phase space volume are concentrated nearby the highest value of your extensive variables. Okay, so that's a property that we try to demonstrated in our homework 2. That basically that's the homework, the first problem of homework 2. So the most important contribution came from this yellow region. So as long as you include this yellow region, you don't need to worry about whether you include part of your configuration just above the lower bound, or you include all the configuration above the lower bound. Okay. So that's basically another important idea that we try to emphasize. Then we try to switch gear to another very important idea, which is the Liouville's theorem. Okay. And what is Liouville's theorem? Basically, it suggests it is discussing the behavior of a mechanical system under the canonical evolution. Which is just described by this sets of equation of motion. Okay. And we did not really prove the Liouville's theorem, but we said that the conclusion of Liouville's theorem is that if you start your system, or like if you have a set of system, basically constrained within a phase space volume gamma 0, as the systems evolve as a function of time, basically this volume of the phase space will evolve from gamma 0 to gamma t. And Liouville's theorem says that this volume will be invariant under the canonical evolution. Okay. So roughly the picture might looks like this. Oops. So here is our phase space. Initially, maybe you have a region like that, and after you evolve by G, basically all the points will start to move. So maybe the shape of the regime will change, but the volume of it will stay the same. Okay. And also, we try to have a if we accept this concept that the volume of the phase space will be preserved under the canonical evolution, one can actually show that, and we roughly give the idea how to prove that the local probability density actually will not change under the canonical evolution, which means that the value of this rho will basically be identical from the initial time to any time during the evolution. So here, what's the meaning of this rho is basically if we try to ask what's the probability of finding a system around a configuration, around a phase space point Cassini nearby a volume d gamma, then the probability can be expressed by this rho. Okay. And this also suggests, if you try to write it in a mathematical way, that is the total derivative of your probability density will actually be 0. Okay. So these two, property are actually the equivalent statement. So today we are going to have a proof 1 for this conserving of the volume of under the canonical evolution, and we'll also give a proof 2 that is more like from the local conserving property. So give these two proof, you can see that why they are equivalent quite intuitively. And from the first and the second property, from the Liouville theorem, you can actually prove that if our probability density function rho, which is at the initial time, it should somehow depends on the microscopic configuration c. But if it depends only on the value of extensive variables, that is, it only depends implicitly by its microscopic configuration c. So if it looks like this kind of function, or maybe I'll just write it explicitly. And here these x are extensive variables. So if it satisfies this type of relation, then from the Liouville theorem, you can prove that the probability density actually have no dependence on t. Okay. So why this third property is important? Because at the thermodynamic system, we usually will specify our system by specifying the extensive variables x1 to xr. So this relation, secretly tells us that it is possible that we can establish a probability description that is independent of time. Okay. So basically, today we are going to show that, and I think in our last lecture we already show how, if we believe Liouville's theorem holds, then we should be able to prove 3 also holds. Okay, so that's basically the roadmap of today's first lecture. Are there any questions so far? So since we live in a relatively high dimensional space, to prove the Liouville theorem using this the approach I'm going to show you, will have a bunch of indexes at different coordinates. So I'm going to simplify it just to focus on the specific pair of momentum and position to show you the idea. And in order to generalize it to a higher dimensional system with a lot of components and a lot of particles, it should be relatively straightforward. So let me just try to start with the setting of the proof. So suppose we consider only one particle and just focus on the one of the component of that particle. So we don't need to worry about the vector. So we will just specify R and P, which is the position and momentum of that particle along a specific direction. Okay, so let's just try to pick one point in this sub space of our phase space, and let's call it a point. Okay, and let me just try to specify the 4 corners by A, B, C, D points. Okay, and at A point we denote this the coordinates of in this phase space to be x0, and this x0 correspond to your position to be at R0 and the momentum to be at P0. Okay, and these 4 points A, B, C, D basically form a rectangular, and we are try to denote the length of the sides to be dr. That's basically this size dr, and this size dp. Okay, maybe I specify it to be dr naught and dp naught. Okay, so in principle, we should be able to specify the 4 coordinates. So, but before I do that, let me try to write down what I just defined. So x naught is just the r naught and p naught. Okay. So the first thing is that we want to discuss how the system evolved under the canonical evolution. So let me just write down the equation for canonical evolution. So in the most general case, I should just be able to put an I as the index. And this Ri dot is basically to some extent, you can consider imagine it as the velocity of Ri, and that's denoted by B. That's we're trying to follow the notation on Postulates textbook. And the Pi dot, which is the time derivative with respect to the time derivative of Pi. So basically, it will correspond to the velocity component of Pi, which is minus partial h partial Ri. So here B is the velocity vector. I'll just remove the vector notation for simplicity. Okay, so now we set our stage that this is just the equations for the canonical evolution, and we have a volume basically right here defined by this A, B, C, D, and the volume of this rectangle is kind of easy. It's just dr naught times dp naught. Okay, and we want to ask how this volume evolved under this canonical evolution. So let me try to be a bit more specific about what are the coordinates. So the coordinates for A is just x naught, which is r naught p naught, and the coordinate for B is also easy to express. We start from x naught, and we just add a vector that's the r naught along the x direction. So let me use I to denote the unit vector along the r direction. And C is x naught plus the r naught I plus the p naught j. Okay, that should also be straightforward. So I'll just write it down. Okay. So we ask, after the time evolve, maybe we'll just use a relatively small time or a short time evolution. Then we ask where these points A, B, C, T will end up to. So that's denoted by A prime, B prime, and C prime, D prime. So let's try to erase this part, just not to make things too complicated. So what do I mean by that is maybe after the evolution, D will move somewhere here, and A will move somewhere here, and C might move somewhere here, and B might move somewhere here. Okay, and the shape of the volume might be a bit distorted, but it doesn't matter. We are just trying to get an approximation about what is the size of this volume. Okay. So let me denote these new points as A prime, and B prime, and C prime, and D prime. Okay, so now we know what we are trying to do. We basically will try to extrapolate the new coordinates by this velocity B. So A prime will be its initial position plus the velocity defined on x naught times dt. And similarly, we'll also have B prime. I'll just write it down. And the idea should be quite straightforward. You just evaluate the velocity around that point and just times the dt and add it to the original position. Okay. So we can ask how to evaluate the volume once these four corners are, moving as a function of time. The simplest way to imagine that is some kind of should be approximately by cross. So b prime minus a prime will be this vector, and b prime minus a prime will be the other vector. And we know in this simple 2D system, the volume is just the cross product of these two vectors. So you just brute forcefully insert everything into this expression. Then you'll see this thing will look like. Okay. And here we introduce some strange p prime. And this p prime is just some point that that's nearby p naught, but it is smaller than the distance between p prime and p naught is smaller than dp. So why we introduce that? Because to some extent, after the system evolved, this gray area might be distorted a little bit, right? So in order to capture that value, you can approximate it by some kind of, good shape, a well-defined real rectangular, not a distorted one. But this estimation will just give you some kind of, approximate idea about how big is the size. But no matter what, since the dt is a small value, so it will require this p. Like if you approximate it by some kind of rectangle, then the rectangle will have only some kind of projection. Maybe I'll just write it down such that it is easier to imagine. How to write it? So it looks a bit. Let me just try to be more precise. This is A to D, and this is A to B. Okay, this is supposed to be the area if we really faithfully apply that. And also we kind of assume that it should be a straight angle here, but let's not worry about that too much. So, but obviously you can see this green area and this gray one is not exactly the same. So how to to some extent approximate that is that you said that, oh, maybe the correct value of the green area should not be take the value of the length of b prime minus a faithfully. Maybe you should cut it to be a smaller piece, and maybe this is the correct p prime value. Oops, I think I labeled it wrong. R prime value, and this is the correct p prime value. Okay, so that's like the approximation or the conceptually idea that what is the meaning of this line. And this is just one projection along the r direction, but you also need to have across another projection, which is dp naught along the j direction. Okay. And again, by similar concept, we require R prime to be not too far away from R naught. Okay. So just very brute force, just expand the brackets. Then what you have is that this volume looks like this. Okay. And of course, you will be evaluated at different points, but as the elements of this area is quite small, so you can think of it as almost approximately evaluated at the same point. And remember, this BR can be defined by partial derivative of your Hamiltonian with respect to momentum. So what you got is something like this. And basically, this thing equal to 0. So so that means that at the leading order, the evolved volume will basically be identical with the gamma 0, basically the initial volume that we start with. But the correction will be due to the change of the shape, a little bit of the change of the shape, and also higher order of the dt power. So because of that, this correction, when the element is going to infinite small, then this correction will be gone. So at the short evolution time dt, we can actually show that the volume is exactly equal to gamma t. So up to some higher order corrections. Yes? 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 You mean the blue one or the blue one? Just means that we randomly pick a small element in the phase space, because in principle, when we have a phase space, like if I have a system, I can tell you what are the possible coordinates and momentum. Then we have a well-defined phase space, right? Then I need to tell you what are the extensive variables, right? I need to tell you what is the volume and what is the energy. Then you are able to tell me, aha, in that phase space, only a part of the phase space satisfy those criteria with specific energy and volume. But the Liouville theorem tells us that under time evolution, this volume is going to be conserved as the function of time is evolving. But the question is how to prove that, right? If you start with the arbitrary volume, then it will be very difficult for you to prove this theorem. So the idea is that you cut this restricted phase space volume into smaller pieces, and these small pieces is just this for demonstrative purpose, I write it as a rectangular. So every arbitrary shape of the volume in your phase space, you can consider it as constructed by smaller pieces of these rectangles. Okay, and if you are able to show that each rectangle after the evolution, it is not going to change its volume, then that means that the sum of each rectangle will also be conserved under the time evolution. So the idea is that maybe we should not deal with the arbitrary shape. We just pick one element that's infinite small, and we ask how it changes as a function of time. If we are able to show that more or less it is basically the same as the time evolved, then we finish our proof. So this is the logic. So we start with some gamma naught, which is small area or a small volume in our phase space, and we ask how it evolved under a very short time. And then we show that basically this volume is conserved. So for a bigger volume, of of course, it will be conserved because bigger volume is just the sum of these small elements.
It's probably also, and it is one particle.
Yeah, we try to simplify it to demonstrate the idea of like one particle, one dimension, right? So this R and P is just a two-dimensional coordinate. Yeah. Yeah, a very small portion of your phase space. But you can ask, if I have n particle or I have 3 components, what happened? Basically, you just generalize this idea, but just put in the more index. One specify how many particles you have, and the other alpha index specify what's the dimensionality of your system. If it is 2D, then you have 2 index. If it's 3D, you have X, Y, Z, things like that. Then, but all these additional index will just make this proof more more troublesome. But the idea is basically the same, because each X there will be a conjugate momentum P, such that you will cancel its contribution at the leading order of this term. So the generalization to a higher dimension is to some extent a trivial generalization, but you need to convince yourself by putting more index inside it. But I'm not going to do that in front of you, because it will be a bunch of index. That's kind of boring. So I just show you the general idea how it works. Okay, good. So are there any other questions? Yes. Is the energy conserved? That's a good question. So when we use this kind of canonical evolution, we implicitly assume that the energy is conserved in this case. But in principle, if there's a non-conserving quantity, the Liouville theorem will not hold as usual. So basically, the idea is that if there's a dissipation, for example, in your system, when the energy is not conserved, usually the most cases is that you have friction or something, such that as the system evolves, the energy is dissipated into the air. So in that case, what is going to happen is that in your phase space, there are some special point that the system prefer to sit on. Okay, so let's try to think about what does that mean. So suppose we have a simple harmonic oscillator, right? And we just said that, if the energy is conserved, then it will be, following the trajectory of a eclipse. So we can ask ourselves, like, if I put a dissipation in the coordinate side, for example, there's a friction on the board or something. So as the system evolves, it will basically, dissipate the energy, and maybe, wait, I think I'm not drawing it right, but the energy will basically decay, and at some point it was stuck there without any momentum, because now every kinetic energy is dissipated away. So that's what is going to happen. So you can imagine that if that kind of situation happen, so for example, you might have various different initial conditions, but every one of it will start to bow around and eventually end up stuck at some real space without momentum. Then the phase space volume looks like it is going to be attracted to certain line or certain points of your phase space. So in that case, your phase space volume is not going to be conserved. So you should not have the conventional Liouville theorem. So at this point, we are assuming that the energy is conserved implicitly by following this canonical evolution. Okay, good question. So are there any other questions? Okay, good. So if not, let's try to go to our proof 2. So the proof 2 is to some extent more elegant because the proof 2 is by observing one thing, that is basically the probability is locally conserved. Okay, so what does that mean? It means that no no probabilities leak out. So we already actually at some point use this condition to analyze our problem. We encounter it first at the random walk problem, where we have a bunch of particles, and we said that it can make varieties move, but it cannot disappear. So at the first chapter or the first few lecture, you have seen this kind of equation. Okay, that's the continuity equation. So if we try to use that kind of idea, that basically we start in RP space, and we have some system with different initial condition, and as the canonical evolution tells us that the energy is conserved, we will basically move from one spot to the other. Okay. And suppose this is the initial space and this is the final space. Okay. And we require that no particle get lost. Here, the particle means like the points in this phase space, which means the trajectory for a specific initial condition of our system. So if we assume that, then the generalized expression for this continuity equation is that the probability density rho should satisfy this high-dimensional version of the continuity equation. Okay. So if we start from here, then we can ask, can we show that d rho dt is 0? That's the question we want to ask. So let me just write down a few steps, then you'll see why it should be like that. So at the right-hand side of the equation, let me just try to write it explicitly by labeling all the 6n components. Okay. Okay, maybe I should just use the usual product, not to confuse everybody. So at this point, when I is labeling from 1 to 3n, it is labeling the coordinates. When we discuss I from 3n plus 1 to 6n, it is representing the momentum pi. Okay. So that's basically a formal rewritten of the right-hand side of the equation. And here the current J is just the probability density times the velocity vector. But now I decompose it into different components. So it will just be VI. Okay. So now, as we mentioned, that we have coordinates and momentum. So maybe we should try to rewrite our dummy indexes to be just let I to run from 1 to 3n. And the first 3n will be just the coordinates. So maybe let me just replace it by Ri. Here's rho, and Vi is just partial H, partial Pi. And the rest of the terms starting from 3 plus 1 to 6n will be this thing. Okay. So so now you can see if you try to use the just differentiate this product, you'll see basically you this expression where you take derivative with respect to rho first. Okay, but there's another term, and basically this thing is 0. So so eventually what you got is, if you shift this term to the left hand side, you have just let me finish this line, and you'll see why this thing is equivalent to total derivative of your density, and it will be 0. Okay, so I think I'll stop here and summarize the result in the next lecture. So see you next after 10 minutes. Yeah. Okay, so I think we just show the proof 2 and get to the important conclusion that the total derivative of our probability density is basically 0 according to the Liouville's theorem. Okay, so basically it is almost the same as the statement 1, and the reason is just simply because if you start with some volume, and maybe there are several points within this volume, say maybe 5 points, and then after the evolution, we said that the area can be distorted, but the volume of this area should be invariant. But also, as we mentioned, that as the system evolves, each point represents one system, and no system can disappear. So the number of initial point, if it is 5, after the evolution, needs to be 5. And if the area is not changing, that means the density must be conserved also. So that's why at the very beginning I said the statement 1 is equivalent to statement 2. And we just show 2 independent proofs. So once you got one of them, you can actually derive the other. Okay. So there are some terminology. So if you try to imagine this, even though in phase space, each point is not a particle, each point represents a system. But if you try to just look at these points and consider it as some kind of mass point, the dynamics of these points can be, imagined as some kind of fluid. Okay. So sometimes people said this kind of evolution governed by canonical evolution actually form a incompressible flow. Okay, it is just a terminology, but it just means dρ dt equal to 0. Okay, so if you read the literature, you see things like that. It just means this property. And because the area is preserved, so if this probability density is uniform, foci in a specific volume gamma, it will stay uniform under the canonical evolution. Okay, so it is almost like a restatement of the same thing, but it kind of suggests that, as I mentioned, it is possible for us to form some kind of probability description of our system. Okay, so now I'm going to just say something without explaining too much about this subject, because even though it is a very interesting subject, but I need to say that it is a little bit more theoretical, so maybe not everybody is interested about that. So I'll just mention some of them. So here, a very good reading material is the chapter 4.2 of Cessna's textbook. So basically, the Liouville theorem is important not only just because it tells us that it is possible for us to form some kind of probability description of our system, but it also connects to the idea of ergodicity. So roughly, the idea of ergodicity is that suppose you have a phase space, and maybe there's a volume in your phase space that is accessible. Whenever we say the system is ergodic, what that means is that if we start from any point in this volume, let's assume that our system starts at some point and at t equal to 0. And as it evolves, it will try to go through this accessible regime in various way. And ergodicity means that basically every point in this volume will be visited as the time is evolving. But the problem is how long does it take? Okay, but that could be quite subtle. But the point is that once a system is ergodic, you can show that actually the time average of your system is equal to the average over this volume gamma with a constant energy. And this kind of averaging over gamma with constant energy, sometimes people will call it the microcanonical ensemble. Okay, we'll discuss more about that, but I just want to say something about this thing from an ergodic point of view. Okay, that's one thing. And the second thing is that the study of ergodicity itself is a big subject. Basically, it is related to how a system thermalize. Okay. It is a problem that is very interesting at the classical level. There are some important work by Fermi, Pasla, and Ulam. And also at the quantum level, it is related to something called eigenstate. Oops. So you might feel like it is quite surprising that even for classical or quantum system, that how a system thermalizes is actually not yet completely solved the problem. So if you are interested about that, there are a lot of things that's waiting to be done. But I just want to say something to tell you that you should not be limited by this course. There are still a lot of things outside there. Okay, and another thing is that, as we mentioned, that if within this regime that every point in this restrictive phase space will be visited at the long time, that's what people said it is a ergodic system. Then the question is, are there systems that break the ergodicity? That is related to the idea of ergodicity breaking. Okay, one of the very important idea related to ergodicity breaking is the spontaneous symmetry breaking. which is a phenomena that happened at phase transition. Okay, we will talk about that later in the course, but I just want to show you, a rough idea. What do we mean by ergodicity breaking in this spontaneous symmetry breaking scenario? So let's just consider we have a bunch of, spins pointing up or down in various way. I don't know, I just randomly draw one, maybe 9 of them. So we can label it out as the spin 1, 2, 3, 4, 5, 6 to 7, 8, 9, something like that. So in principle, if you have a larger system, you just have a bunch of spins, okay? So how to specify the configuration of these spins? There's a very interesting way. If you came from computation science, you know this thing is called binary tree. So the idea is that you start from some point and you draw some line which represent a choice. So one choice must be positive and the other choice is negative. So let me try to draw a little bit more to explain why this binary tree is useful to demonstrate the idea that we want to discuss about. Maybe I'll just draw another one. Okay, so basically, you try to follow the path, and every time there's a branch that is of order 2. So that's why it's called binary tree. So let me define at the right branch. That's basically what's in the up is going to be the plus branch. And on the other side is similar. Okay. So for example, for our suppose we have only, I don't know, 4 spins. If I follow this path, it just tells me what is the spin configuration of my first spin, my second spin, and my third spin, and my fourth spin. Okay. So if I just follow this tree, it will give me something like 4 spin up to here. But if I choose another path, I don't know, for example, maybe I like to go this way, then I can say this is my first spin, second spin, third spin, and fourth spin. Then what I should get is minus, plus, and minus. Okay. So you can convince yourself that, at the end of each branch, you basically specify what is the spin configuration for your system. Okay. It's not too complicated. But why I'm trying to say that is because from this rough picture, you kind of can see that, more at the top right corner is something that is more plus, right? Because you have more plus somewhere there. And at the more lower left bottom, you'll have more minus because of our definition. Okay. So suppose you consider your configuration for this very simple 4-spin configuration. We will have 2 to the 4 configurations. That's basically 16 of them. You can think of it that as if you have divided your possible configuration or your phase space to be 2 pieces. One is with more plus, and the other is more minus. Okay. So what is the spontaneous symmetry breaking or ergodicity breaking in this scenario is that for the model, which is called the Ising model, like one of the typical model is Ising model, that they just have the spin product with each other. And here this product is just nearest neighbor interaction. But we'll see that a bit later. But the point is that for this particular model, when you lower the temperature, you will go from the paramagnetic phase into the ferromagnetic phase, which means that all the spin will line up together, okay, in order to minimize their energy. And one question you need to ask yourself is that, this Hamiltonian looks like it has a specific symmetry. That's basically, if I flip all the spin from upward to downward, basically the energy doesn't change. So how come at the low temperature that the system prefer one direction than the other? Okay, so the idea is that for this 4-spin configuration, we can explicitly show that by this tree structure, we have some kind of 2 branches of spin configuration. But when the system size is larger and larger, you'll see that this tree will grow to be exponentially large. And when the tree is exponentially large, it is going to be exponentially difficult to go from the branch with more plus to the branch of more minus. So that means your phase space is to some extent becoming separated into 2 subspace. So that's why people say this thing is called ergodicity breaking. Okay, so this is the simplest case for ergodicity breaking, and also with important implication about the spontaneous symmetry breaking. And there's another famous topic since last year is something called spin glass. Okay, so if you understand why spontaneous symmetry breaking in this Ising's model, basically the symmetry is V2, and spin glass basically is a situation where your phase space is broken in a very weird situation that they break into local regimes, and all these local regimes are basically cannot connect with each other by usual standard evolution. So all these lines represent ergodicity breaking. And of course, it does not really break in this specific pattern. I just want to tell you the idea that you will become a bunch of patches in your phase space. And how to characterize this kind of spontaneous symmetry breaking behavior basically leads to the Nobel Prize of last year. Okay. So another thing that's related to Liouville theorem is a concept called Poincare recurrence theorem. The idea is also simple. Suppose you start from t equal to 0, you start from one point of your phase space. And the theorem just tells you that if you wait long enough, basically your system will do some very crazy evolution in your phase space. But as you wait long enough at t equal to t, then this system will come back to where it is. Okay, but the question is how long is long enough? Of course, there will be some other details that I'm not going to talk about. And also there's a very interesting theorem called H theorem. Basically, you can show that, sorry, I think I should use total derivative is greater than or equal to 0, which just suggests that entropy will always be an increasing function as a function of time. The first thing you need to be careful is that if I tell you that there's a Poincare theorem, that when I wait long enough, the system will get back to where it is. That means that something is wrong about H theorem, because entropy cannot increase, but all of a sudden it came back to what is the value of the entropy. So at some point, entropy will be decreasing. Does it make sense? So that's a question mark that's leave for you if you are interested to explore. So I think there are a lot of interesting fundamental questions about statistical mechanics, but unfortunately it is statistical mechanics 1, so I'm not going to talk too much about that. Okay, good. So now we are going to explore the second question that I left without explanation. That's basically the variational principle of entropy. So we just showed that if we try to follow Boltzmann's postulate and we use Liouville's theorem, to justify the question about Y-phase space. And I think now the answer should be apparent because we have a specific set of equation of motion that is this canonical evolution, and we can show that there are some nice property about the probability density function, which suggests that we might be able to form some probability description, which is, we haven't shown it, but it kind of suggests it is possible. But we also want to ask, suppose we follow this Boltzmann's postulate, we can ask, can this expression really give us a consistent picture with the variational principle as we did in the thermodynamics entropy?